This episode is brought to you by Cisco Educational Premium. Did you know that Planck units are units of measurement in particle physics and physical cosmology? Planck units are a set of units of measurement defined exclusively in terms of four universal physical constants, in such a manner that these physical constants take on the numerical value of 1 when expressed in terms of these units. Originally proposed in 1809 by German physicist Max Planck, these units are a system of natural units because their definition is based on properties of nature, more specifically the properties of free space, rather than a choice of prototype object. They are relevant in research on unified theories such as quantum gravity. The term Planck scale refers to quantities of space-time energy and other units that are similar in magnitude to corresponding Planck units. This region may be characterized by particle energies of around 10 raised to 19 gigafolds or 10 raised to 9 joules. Time intervals of around 10 raised to negative 43 seconds and lengths of around 10 raised to negative 35 meters, approximately the energy equivalent of the Planck mass, the Planck time, and the Planck length, respectively. At the Planck scale, the predictions of the standard model, quantum field theory, and general relativity are not expected to apply, and quantum effects of gravity are expected to dominate. The best known example is represented by the condition in the first 10 raised to negative 43 seconds of our universe after the Big Bang, approximately 13.8 billion years ago. The four universal constants that by definition have a numerical value of 1 when expressed in these units are 1. The speed of light in a vacuum c. 2. The gravitational constant g. 3. The reduced Planck constant h. And 4. The Boltzmann constant k sub b. Planck units do not incorporate an electromagnetic dimension. Some authors choose to extend the system to electromagnetism by, for example, adding either the Coulomb constant k sub e is equivalent to 1 on 4 pi E naught or electric constant E naught to this list. Similarly, authors choose to use variants of the system that give other numerical values to one or more of the four constants we have seen. Any system of measurement may be assigned a mutually independent set of base quantities and associated base units, from which all other quantities and units may be derived. In the International System of Units, for example, the SI base quantities include length with associated unit of the meter. In the system of Planck units, a similar set of base quantities and associated units may be selected, in terms of which other quantities and coherent units may be expressed. The Planck unit of length has become known as the Planck length, and the Planck unit of time is known as Planck time, but this nomenclature has not been established as extending to all quantities. All Planck units are derived from the dimensional universal physical constant that define the system, and in a convention in which these units are omitted, that is treated as having dimensionless value 1. These constants are then eliminated from equations of physics in which they appear. For example, Newton's law of universal gravitation. Of course, these Planck constants appear, so they are eliminated as shown by the second equation. Both equations are dimensionally consistent and equally valid in any system of quantities, but the second equation with g absent is relating only dimensionless quantities, since any ratio of two like dimensioned quantities is a dimensionless quantity. If By shorthand convention, it is understood that each physical quantity is the corresponding ratio with a coherent Planck unit, or an I quote expressed in Planck units. The ratios we have seen may be expressed simply with the symbols of physical quantity without being scaled explicitly by their corresponding unit. This last equation without G is valid with F prime, M1 prime, M2 prime, and R prime, paying the dimensionless ratio quantities corresponding to the standard quantities written, for example, F prime being F or F prime being F on Fp, but not as a direct equality of quantities. This may seem to be like what setting the constant Cg, etc. to 1 if the correspondence of the quantities is thought of as equality. For this reason, Planck or other natural units should be employed with care, referring G is equivalent to C is equivalent to 1. Paul S. Wesson wrote that mathematically it is an acceptable trick which saves labor. Physically, it represents a loss of information and can lead to confusion. The concept of natural units was introduced in 1874 when George Johnston Stoney noted that electric charge is quantized. Derived units of length, time, and mass, now named Stoney units in his honor. Stoney chose these units so that G, C, and the electron charge E would be numerically equal to 1. In 1899, 1 year before the advent of quantum theory, Max Planck introduced what became later known as Planck constant. At the end of the paper, he proposed the base units that were later named in his honor. The Planck units are based on the quantum of action, now usually known as the Planck constant, which appear in the Wien approximation for blackbody radiation. Planck underlined the universality of the new unit system, writing, "It is possible to set up units for length, mass, time, and temperature, which are independent of special bodies or substances, necessarily retaining their meaning for all times and for all civilizations, including extraterrestrial and human ones, which can be called natural units of measure." Planck considered only the units based on the universal constants GH, C, and Kb to arrive at natural units for length, time, mass, and temperature. These definitions differ from the modern ones by a factor of root 2 pi because the modern definitions use reduced Planck's constant rather than Planck constant. Unlike the case with the International System of Units, there is no official entity that establishes a definition of a Planck unit system. Some authors define the base Planck units to be those of mass, length, and time, regarding an additional unit for temperature to be redundant. Other tabulations add, in addition to a unit of temperature, a unit for electric charge, so that either the Coulomb constant, Ke, or the vacuum permittivity, E naught, is normalized to 1. Thus, depending on the author's choice, this charge unit is given. Some of these tabulations also replace mass with energy when doing so. The Planck charge, as well as other electromagnetic units that can be defined like resistance and magnetic flux, are more difficult to interpret than Planck's original units and are used less frequently. In SI units, the values of CH, E, and KB are exact, and the values of E naught and G in SI units respectively have relative uncertainties of 1.5 times 10 raised to negative 10 and 2.2 times 10 raised to negative 5. Hence, the uncertainties in the SI values of the Planck units derive almost entirely from uncertainty in the SI value of G. Compared to the Stoney units, the Planck base units are all 1 on root alpha, approximately 11.7 times larger. In any system of measurement, Units for many physical quantities can be derived from base units. The table has a sample of derived Planck units, some of which are seldom used. As with the base units, their use is mostly confined to theoretical physics because most of them are too large or too small for empirical or practical use, and there are large uncertainties in their values. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.